Hello everyone. Today we shall discuss the chapter that is work, energy and power. In the previous class we have already discussed about work, and today I am going to discuss about power and energy. Before that we will do an example of uh, work done, how to find work done. So there is a question. First we will take a question, after that we will solve the question, how to solve this question of work. After that I will go to another section, that is how work can be find out. We already told about this, how work is done. Now today I am going to discuss about kinetic energy, and generally we follow the NCERT syllabus. So go to the NCERT syllabus and get all the problems, all the solutions there. Now we are going to discuss these things, that is this one we are dealing with, right? So here you see that today we are going to discuss with this one, that is kinetic energy, right? What we'll get in kinetic energy, that is important for us, right? Now today we are discussing work, power, energy. In the previous class we have already discussed work. Today's chapter is work, power and energy. Work, power and energy. Now today we are going to discuss about kinetic energy. Kinetic energy, that first of all you have to know whether kinetic energy is scalar quantity or vector quantity. Actually kinetic energy is a scalar quantity. Kinetic energy is a scalar quantity. Because kinetic energy has only magnitude and no direction. Because kinetic energy has only a magnitude, but no direction. So we can say that kinetic energy is a scalar quantity. How to find the kinetic energy? The kinetic energy of an object is a measure. The kinetic energy of an object, the kinetic energy of an object is a measure of the work, an object can do, an object can do by the virtue of its motion, by the virtue of its motion. So if there is a motion, we find the kinetic energy, and kinetic energy can be represented as kinetic energy. The formula for kinetic energy is half 1 by 2 into m into v square, where m is the mass, m is equal to mass of the object, and v is the velocity of the object. In this way you can find the kinetic energy of any particle, right? This is the way. So this notion has been intuitively known for a long time. The kinetic energy of fast flowing stream has been used to grind corn. sailing ships employ the kinetic energy of the wind, right? In this way, we can find the kinetic energy, right? These are the way in which we find kinetic energy. Now, if we want to find work done by variable force, and today I am going to discuss about work done by this is the definition of kinetic energy. So kinetic energy is half m square. This is the formula for kinetic energy, where m is the mass and v is the velocity of the object, right? So this is kinetic energy. Now we are going to discuss another important thing, that is work done by variable force. In the previous class we have learnt about work done by a constant force, and today I am going to discuss about work done by variable force. Work done by variable force. Work done by a variable force. Variable force. What is that work done by a variable? That if force is changing, in that case what we will get, that is work done by a variable force. Actually, a constant force is rare. A constant force is rare. It is the variable force which is commonly more encountered. It is the variable force. It is the variable force. It is the variable force. It is a variable force which is more commonly encountered, which is more commonly encountered. Now we are going to find this. Now we are drawing a graph or finding the work done by variable force. Suppose this is the graph, right? And suppose this type of graph is here. How to find? This is the force. You see, the force is variable, f of x in the y direction, and we are taking this one. This is xi initial, and this is xf that is final, right? So here we will take an area, a small part. We divide this area into thin sheets like this, and we find the area of this part and integrate it to get the whole area, right? What is that? This area will be area equal to del A. Del A is equal to fx del x. F into x into del x, change in x, right? This is the formula for area. Now we'll find that if here this figure 5.3, in figure 5.3, figure 5.3 is a plot of a varying force, of a varying force in one dimension, Then find what is the value of work done by variable force. If the displacement, suppose this displacement is very small, del x, this is del x, right? Suppose if the displacement, del x is small, we can take the force, we can take take the force Fx as approximately constant, as approximately constant. If the del x is small, then Fx can be taken as an approximately constant, and the work done is there, and the work done is then del W equal to Fx into del x. Fx into del x. This is the work done. When this del x is small, at that time we can take Fx as constant. At this point, you see, this is the point at the point of del x. At this point, Fx is constant, right? We can take approximately, it can be taken as a constant. And in the successive rectangular areas, suppose we have many rectangular areas, 1, 2, 3 like this, successive. So we will add by integration all the successive rectangles. All the successive integrals will add and getting a summation or integration of the whole work. These are the various rectangles, and if we add all of them, we'll get the total work, right? So we'll integrate this one from xi to xf, right? So adding successive rectangular area, adding successive regular areas in figure 5.3, we get the total work done, as W is equal to summation Fx del x, and it varies from xi initial to x final. This is the total work. Where the summation is from the initial position, from the initial position xi to the final position xa. In this way we get the total work done, right? If the displacement allowed to approach 0, now we are getting to the integration part, right? So if the displacements are allowed to approach 0, if the displacements are allowed to approach 0, if the displacement allowed to approach 0, then the number of terms, then the number of terms in the sum, number of terms in the sum increases without limit, increases without limit, increases without limit. But the sum approaches without limit, but the sum approaches, but the sum approaches a finite value, a definite value, approaches a definite value equal to the area, equal to the area under the curve, that is the total work done. Then the work done is W is equal to summation of limit del x tends to 0 fx del x, and b varies from xi initial to x final. It can be changed into integration. This is the definition of integration also, that xi to xf, and this is fx dx. This is the work done we get after summing all the rectangle, right? And here where lim stands for the limit, of the sum when del x tends to 0. So you can find the work done for a variable force. Thus for a varying force, the work done can be expressed, the work done can be expressed as a definite integral, as a definite integral of force, over displacement. So you are getting this one, integration fx dx, where x varies from xi to x final. So we are getting, if we integrate this one, what we are getting, you see here. So the area under the curve is exactly equal to the work done by fx. So if we find the area under this curve, this is suppose xi, this is xf, and this is the curve. And if we integrate from xi to xf, the area under this curve will get the total work done, right? So what we are getting here, you see that this is the work done, that is integration fx. This is the work done for a variable force. So the shaded rectangle, here you see the shaded rectangle, this is figure 5.3. Figure 5.3. The shaded rectangle represent the shaded rectangle. The shaded rectangle represents the work done. Represent the work done by the varying force, by the varying force Fx over the small displacement del x. That is, we are getting del w is equal to fx del x, right? Number 2, this is A. Number B is adding the areas of all the rectangles. We've already told you that these are rectangles, all are rectangles, and this is the main rectangle. This is del x, and this the varying force is constant at this, that is fx. For a small del x, fx is constant at that time. Therefore, the integration of work done equal to fx dx xi to xf. Adding the areas, number B is adding the areas of all the rectangles, we find that for del x tends to 0, the area under the curve, the area under the curve is exactly equal to the work done, by fx. So we find this area, this work done, as this is the integration of fx dx. This is the work done for a variable force. This is the formula to find work done for a variable force. That is to find the area under the curve. So this is the formula for work done for a variable force. What is that? W fx dx, it varies from xi to xf, right? This is the way to find the total work done. Now we will find work energy theorem for a variable force. In the previous class we have already learned work energy theorem for a constant force. Now we are getting another important thing, that is work energy theorem for a variable force, right? Let us find what is that. Work energy theorem for a variable force. The work energy theorem, the work energy theorem for a variable force, for a variable force. The work energy theorem for a variable force. Now we are now familiar with the concept of work and kinetic energy. To prove the work energy theorem for a variable force, we are now familiar with the concepts of work with the concepts of work, with the concepts of work and kinetic energy and kinetic energy and kinetic energy to prove the work energy theorem, to prove the work energy theorem, the work energy theorem for a variable force, for a variable force. We are now familiar with the concepts of work and kinetic energy to prove the work energy theorem for a variable force. We continue ourselves to one dimension. We continue ourselves to one dimension, the time rate of change of kinetic energy, the time rate of change, the time rate of change of kinetic energy, the time rate of change of kinetic energy is dk by dt. This is the time rate of change of kinetic energy. Therefore, we can write ddt of, and what is the kinetic energy? Half mv square, half mv square. Since K is equal to kinetic energy we have taken as half mv square. Therefore, this is the definition of kinetic energy, that is half mv square. Now, if we differentiate this one, since m is a constant, we can take it out the m as outside, right? And dt of v square, if we integrate this dt of v square, then we are getting 2 into dv dt, that we are getting, right? Therefore, we are getting 2 into dv dt, right? That is, m is outside, 1 by 2 into, if we differentiate v square, you see 2 dv dt, 2 dv dt, 2 dv by dt, right? So, 2 v dv dt, it can be defined in this way. Again, you see here, this is not to, again I am differentiating this one. You see here, v square. What is the differentiation of v square? Actually, the differentiation of v square is, we write this differentiation that d dt of v square, then it will be equal to 2v dv dt. This is the differentiation of v square, 2v dv dt. So we'll put it here. Half is also constant, it can be taken out, right? So we can write half into 2 into v into dv into dt. These two will cancel out. So we are getting m dv by dt into v, right? Or you can write dv dt means acceleration, therefore m into a into v, or we can m means f dot v, that is from Newton's second law, from Newton's second law. From Newton's second law, we are getting this value. F V, or you can write is equal to F, and V can be different derivative as dx by dt. Rate of change of position with respect to time, that is velocity. Therefore, we can write F dx by dt. All you have to write in step by step. So you can write therefore that dk by dt equal to this one. So we can write dk equal to this dt, this dt will cancel. Therefore, we write dk is equal to f dx. F dx. So we are getting dk is equal to f dx. This is equation 1. Right? So in the next page we are writing dk equal to f dk, f dx. Thus dk is equal to f dx. Integrating from the initial position, from the initial position xi to final position xf, we have integration of dk x initial to x final is equal to integration of x initial to x final f dx. This can be written as ki because this is initial ki and this is final ki, right? Therefore, where ki and kf are the initial and final kinetic energies, corresponding to xi and xf, right? Or you can write it here as if integrate this one, we are getting k final minus k initial is equal to integration from xi to xf f dx. This is the what we get, and it also from the f plus dx is the work done. Therefore, or you can write it here as kf minus ki is equal to work done. Because in the previous case we found that work done is defined in this way for a variable force, right? Therefore, since work done is equal to xi to xf f dx, this is the work done. So kf minus ki equal to w, right? Thus work energy is proved for a variable force. Thus work energy theorem is proved for a variable force, right? Proved for a variable force. And here is we while the work energy theorem is useful in a variety of problems, it does not in general incorporate the complete dynamical information of Newton's second law. It is an integral form of Newton's second law. Newton's second law is a relation between acceleration and force at any instant of time. Work energy theorem involves an integral over an interval of time. In this sense, the temporal information contained in the statement of Newton's second law is integrated over and is not available explicitly. Another observation is that Newton's second law for 2 or 3 dimensions is in vector form, whereas work energy theorem is in scalar form. In the scalar form, information with respect to directions contained in Newton's second law is not present, right? So this is the concept of work energy theorem. Now we will write the various points again. Here you see what we find from this here, that while the work energy theorem, while the work energy theorem, while the work energy, while the work energy theorem, while the work energy theorem is useful in a variety of problems, in a variety of problems. It does not, in general, it does not in general incorporate the complete dynamical information of Newton's second law. It is an integral form. It is an integral form of second law. It is an integral form of Newton's second law. Newton's second law. Newton's second law is a relation. Newton's second law is a relation. Relation between acceleration. Between acceleration and force. At any instant of time. Work energy theorem involves an integral over an interval of time, over an interval of time. In this sense, the temporal time information contained in the statement of Newton's second law is integrated over and is not available explicitly. Another observation is that Newton's second law for two or three dimensions is in vector form whereas the work energy theorem work energy theorem is in scalar form work energy theory is scalar form. In the scalar form information with respect to directions contained in Newton's second law is not present. So here we find that the work energy theorem is in scalar form, but in 2 and 3 dimension the second law is in vector form, and there is a contradiction here, right? So we can say that in vector form, that is Newton's second law for 2 or 3 dimension is in vector form, whereas the work energy theorem is in scalar form. In the scalar form, information with respect to directions contained in Newton's second law is not present. So there is a contradiction here for that, right? In this way you can define this one, that the work done by a variable force. So today we have discussed about kinetic energy and work done by a variable force. Thank you everybody for watching this video. So what we get at the end, that though work energy theorem is in scalar form, but Newton's second law of motion shows direction. So there is a contradiction here for work energy theorem for variable force, right? Because we have considered here only the one-dimensional motion. But if we consider 2 or 3-dimensional motion, then a direction is concerned. But in this case, here you see that in scalar form information with respect to direction contained in Newton's second law is not present, right? There is another observation is that Newton's second law for 2 or 3 dimension is in vector form, whereas the work energy theorem is in scalar form, and that is the contradiction between the two. In the scalar form, information with respect to directions contained in Newton's second law is not present, right? Okay, thank you everybody for watching this video.